if you stand at the base of like a 50-story skyscraper, it just feels like this unyielding mountain of steel and glass.
Yeah, it really does.
It
Yeah.
looks completely permanent, right? Like it just sprouted from the earth, fully formed. But if you were actually standing on that plot of land on day one, you wouldn't see a building at all. You'd see just thousands of tons of this sloshing, chaotic liquid rock.
Right, the concrete. It is, it's basically the ultimate structural blank slate. I mean, before concrete cures, it's essentially a highly corrosive mud that just wants to flow absolutely everywhere except where you actually want it to go.
Exactly. And figuring out how to stop that liquid from just completely collapsing and, spilling out into the streets is arguably one of the greatest, most stressful magic tricks in modern engineering.
Oh, without a doubt. It's a massive challenge.
So today, we are unpacking exactly how that trick is performed. For anyone listening who, looks up at a massive city skyline and thinks, how do they actually pull that off? This deep dive is for you. We're pulling from a really fascinating technical guide by Eleanor Industries.
Right, the one titled Aluminium Extrusion for Formwork, Complete Guide for Modern Construction.
That's the one. And our mission today is to uncover this hidden, high-tech manufacturing process that is secretly allowing our modern cities to be built, faster and taller than ever before. So, okay, let's unpack this. Because aluminium extrusion for concrete formwork sounds like something deeply buried in a dry engineering textbook.
It does sound a bit dense, yeah.
It really does.
Yeah.
But it is actually the ultimate life hack for mega construction projects. It's the invisible backbone of the modern built environment.
It really is. And to fully appreciate the magnitude of this engineering hack, you really have to understand the centuries-old nightmare that builders have been trapped in. Because like you mentioned, concrete is a liquid when it arrives on site.
Right, just a giant puddle of heavy mud.
Exactly. So to get a perfectly straight 50-story vertical wall out of liquid rock, you need a mold. And the industry calls these temporary molds formwork. It's basically the rigid shell that holds the wet concrete in place.
Okay, got it.
But it's not just holding it, right? It has to actively fight back against the immense hydrostatic pressure of all that liquid weight.
Well, let's break down that pressure for a second, because we aren't just talking about, like, a heavy bucket of water here.
Far from it. I mean, hydrostatic pressure basically means that the deeper the liquid gets, the more it pushes outward against the walls holding it. So if you pour a 10-foot concrete column, the fluid pressure at the very bottom of that column is trying with literally thousands of pounds of force to burst the mold wide open.
Wow.
Yeah, and the mold has to stay perfectly still without bulging even a fraction of an inch until the concrete chemically hardens.
So historically, I imagine figuring out what to actually build that mold out of has been a massive headache. Like, the starting point for most of human history was just wood, right? Timber formwork.
Yeah, wood was the go-to for a long time.
Which, I mean, makes total sense on a basic level. Wood is cheap. You can cut it to size right there on the job site with a saw, and it's everywhere. But when you try to scale that up to a modern high-rise, timber had some pretty glaring, fatal flaws.
It really does. The main issue is that timber is porous. It's organic. So when you trap thousands of pounds of wet, chemically caustic concrete against a wooden board, the wood immediately starts absorbing all that moisture.
Oh, right. So it just acts like a giant sponge.
Exactly. It warps, it splinters.
Yeah.
Honestly, you pour concrete against it maybe 2 or 3 times, and the wood is basically destroyed. It has an incredibly low reuse cycle.
I was trying to picture the frustration of this, and it's kind of like baking a cake in a flimsy cardboard baking pan. Like, sure, it holds the batter once, but it gets soggy, bulges in the middle, and it's completely ruined after you use it just one time.
That is a perfect analogy. And on top of that, because wood has natural grain and knots, it leaves this really inconsistent, rough finish on the dried concrete. So you end up with a wall that looks terrible.
Which means you probably need, like, an army of plasterers to come in and smooth it out later.
Exactly. It's a huge waste of time and labor. So if we connect this to the bigger picture, builders eventually got tired of the cardboard pan and they pivoted to metal. Specifically, they transitioned to steel formwork.
Okay, which solves the weakness problem. Steel obviously doesn't warp from wet concrete. It has, incredible load-bearing capacity.
It definitely solves the weakness problem, but it introduces a completely new bottleneck, which is gravity. Steel is just devastatingly heavy. And think about what was happening globally during this transition.
Right, urbanization was exploding. Cities were running out of horizontal space.
Exactly. We had to build vertically. The demand for massive, complex structures just skyrocketed. But steel formwork requires immense manual labor, and you are constantly dependent on cranes to move anything.
So it's basically like upgrading from the cardboard baking pan to a massive, solid cast iron cauldron.
Yeah.
Like, yes, it works beautifully. The cake is never going to break it, but it is utterly exhausting for a baker to lug a massive cast iron cauldron of 50 flights of stairs every single day.
Right, you just can't scale that cast iron cauldron approach when you're trying to build a megacity on a really tight deadline. The manual fatigue alone slows the project to a crawl. So the construction industry basically hit a physical limit. They desperately needed a Goldilocks material.
Something right in the middle.
Exactly. They needed the unyielding strength and that smooth finish of steel, but at a fraction of the weight. And that desperation is really what prompted the shift to advanced aluminium formwork systems.
Which, okay, this is where my brain immediately threw a red flag while reading the article. Because when I hear the word aluminium, I just think of soda cans.
Most people do, yeah.
Right. I think of something I can easily crush against my forehead. So the idea of using this soda can metal to hold back thousands of tons of skyscraper concrete just sounds like a recipe for a catastrophic blowout. But the Eleanor Industries guide points out that the secret isn't just the raw metal itself, it is how that metal is manufactured.
Yes, exactly. And that brings us to the science of extrusion. Extrusion is the real mechanical magic trick here because it fundamentally changes the structural profile of the metal.
Okay, I need you to explain this to me.
Yeah.
Because reading the technical description of extrusion like taking heated aluminium billets, which are basically big solid logs of metal, right?
Right, solid logs.
And pushing them through a specifically shaped die, it sounds exactly like playing with a childhood Play-Doh fun factory.
I love that comparison.
You know what I mean? You push the lever, the mushy stuff goes through the star-shaped hole, and you get a long star-shaped noodle. But how on earth does squeezing soft metal through a hole create something strong enough to support a building?
Well, the Play-Doh analogy is mechanically spot on for the basic concept. You are indeed forcing material through a profile, but the engineering context is what separates a plastic toy from heavy industry. Let's just start with the material itself. We aren't extruding the same flimsy metal used in a soda can.
Okay, so what are we using?
The construction industry relies on very specific, high-strength alloys, most notably the 6061 and 6063 series mentioned in the guide.
And what do those numbers actually mean chemically? Like, why not just use pure aluminium?
Because pure aluminium is way too soft, those numbers actually represent a very specific recipe. So alloy 6061, for instance, blends the base aluminium with magnesium and silicon.
Oh, okay. What do those do?
Well, the magnesium dramatically increases the metal's structural strength. That's what allows it to take heavy impacts on a job site without shattering. And the silicon lowers the melting temperature just enough to make it extrudable, while also giving it an incredibly high resistance to corrosion.
Which I guess is vital when you're constantly bathing these pieces in wet, highly alkaline concrete.
Absolutely. So the molecular recipe is doing a ton of the heavy lifting before we even shape it. That's the foundation. Now, you add the extrusion press. The facilities manufacturing these profiles, like the massive hubs operating in Gujarat and India, they are not using small machinery.
Right. These aren't tabletop tools.
Not at all. Picture a hydraulic press the size of a 3-story building. They take that 6061 billet, they heat it up to around 900 degrees Fahrenheit, so it's not a liquid, it's just glowing hot and highly malleable, and they ram it through a hardened steel die using thousands of tons of pressure.
And because of that immense pressure, I assume we aren't just creating a solid star-shaped noodle like the Play-Doh toy?
Far from it. That pressure allows engineers to design dies that extrude incredibly complex, hollow geometric shapes. You can extrude a profile that has, like, internal honeycomb webbing, reinforced corners, and integrated interlocking channels all in one piece. Yeah, you're taking a lightweight metal and engineering its internal geometry so it punches way above its weight class. And furthermore, doing this under staggering pressure creates microscopic precision. The dimensional tolerances are just incredibly exact.
Meaning, when you take two of these extruded pieces and put them next to each other on a job site, they fit together flawlessly.
Exactly. There is zero wiggle room.
Zero.
None. And that dimensional accuracy is the absolute key to the load-bearing capacity. When the pieces lock together perfectly, the kinetic energy of the wet concrete is distributed evenly across the entire system.
Okay, that clears up the whole soda can confusion entirely. We are essentially forging complex geometric trusses out of a superalloy. So let's take these newly forged profiles out of the factory and actually put them on a job site. Let's look at the anatomy of this system because honestly, reading about it, it just sounds like a high-stakes industrial-sized Lego set.
It is entirely modular, yeah. And understanding how these parts interact really requires looking at the journey of the forces at play. Imagine you are the wet concrete that just got poured. You are pushing outward with immense force. The very first thing you hit is the aluminum panel.
Okay, the panel.
Yeah.
That's the broad, flat surface shaping the wall, right?
Yes.
But if it's just a lightweight, flat panel, why doesn't it just bow outward in the middle from all that hydrostatic pressure we talked about earlier?
Because the panel is never acting alone. The second the concrete pushes against the panel, all that kinetic energy is immediately transferred to the extruded beams and supports that are locked in right behind it.
Wow.
And these beams are those complex geometric profiles we just discussed. They catch all that outward pressure and basically channel it downward into the ground or into the previously cured floor below.
So the panels are just the face, but the beams are the actual muscle holding the line.
Exactly.
And that takes care of the vertical walls. But what about the horizontal spaces, like the floors and ceilings?
Right. That force is handled by the deck panels. Pouring a multi-story building means you need to support a massive horizontal concrete slab suspended completely in midair.
Which sounds terrifying.
It is. These deck panels have to hold up the sheer dead weight of the wet concrete from underneath while simultaneously supporting the dynamic weight of a crew of workers just stomping around on top of it.
Right, guys with boots and tools.
Yeah. But the strength-to-weight ratio provided by the 6061 alloy makes this possible without needing a dense, heavy forest of steel support beams cluttering up the floor below.
And keeping this entire structure rigid are the wall formwork profiles and the corner sections, right? The guide mentioned extruded angles that ensure the walls are perfectly plumb-like, exactly 90 degrees. It's just fascinating how every single piece cascades into the next.
It really is. You see the genius of the extrusion process when all these components lock together? Panels, beams, deck supports, and corner sections, they all pin together with zero gaps. Because if there were gaps, the liquid concrete would just bleed through and create a structural weak point.
Now, here's where my mind was truly blown reading through the advantages of this system. Because those tight tolerances mean the Lego pieces fit together without any seams, the resulting concrete finish is unbelievable. You peel the aluminum mold away, and the concrete wall is perfectly smooth. The guide points out that builders often don't even need to do any additional plastering work.
Yeah, the economic ripple effect of that single detail is staggering.
I was going to say, like, what does that actually look like for a real construction timeline?
Well, think about a 50-story residential tower. Traditionally, after you pour a floor and let it dry, you have to bring in an entirely separate crew of plasterers.
Just to fix the ugly walls.
Right, and they spend days scraping, patching, and smoothing every single wall and ceiling before you can even think about painting or installing fixtures. But if you completely eliminate that step because the aluminum formwork left a glass-smooth finish right out of the gate, you are shaving weeks, potentially months, off a mega project.
Wow. Now, as someone anticipating a catch here, if the metal is that perfectly smooth, doesn't the wet concrete just sort of glue itself to the aluminum?
Yeah.
I've tried to get dried cement off a smooth shovel at home, and it feels like it's fused at the atomic level.
That's a really great observation. Bare concrete absolutely wants to stick. But because the extruded aluminum is entirely non-porous, unlike wood, which sucks the water in and binds to it, builders simply coat the aluminum panels in a very light formwork release agent before they pour.
Oh, so it's literally akin to greasing a baking pan.
Exactly like greasing a baking pan. Because the metal has no pores, that thin barrier ensures the concrete never actually bonds to the aluminum. Once the wall cures, workers simply unpin the joints and the panels just peel away cleanly.
Which leads right into the biggest advantage of all, reusability. We talked about wood being ruined after just a few pours.
Right, but the 6061 and 6063 alloys are virtually immune to the moisture and the alkaline chemicals in the concrete. You can use this exact same setup hundreds of times without the metal fatiguing, warping, or losing its geometric precision.
That's incredible.
You pour floor one, let it cure, unpin the lightweight aluminum panels, have your crew literally carry them up the stairs by hand.
No waiting for massive cranes to haul heavy steel cauldrons around.
Precisely. You pin them together on floor two and you pour again. It fundamentally accelerates the floor-by-floor cycle time.
So let's zoom out for a second and look at the macro impact of this. Because cutting plastering crews and speeding up floor cycles isn't just about, saving a developer some money on an apartment block. When you scale these efficiencies globally, it feels like it is actively reshaping how fast human infrastructure can be deployed.
Oh, absolutely. And the applications go far beyond just high-rise residential buildings, though that is obviously the most common use case for repetitive floor cycles.
Mhm.
We're seeing these extruded systems deployed in massive commercial complexes, too.
Right.
Those buildings often integrate the aluminum formwork right alongside extruded aluminum glazing and glass profiles to create those seamless modern facades we see everywhere.
And it's not just buildings either. The material highlights major public infrastructure like bridges, underground metro stations, massive transportation hubs, places that require heavy-duty hardware profiles to handle extreme structural loads, but still demand really fast construction timelines.
Exactly. The Eleanor Guide lays out a comparison chart that really frames why this shift is permanent. If you grade the materials on a curve, timber has low reusability, limited precision, and slow construction speed.
Your cardboard pan.
Right. Then steel fixes the precision and reusability, but the sheer weight keeps the construction speed moderate. But aluminum formwork just sweeps the board. Very high reusability, excellent microscopic precision, and rapid construction speed.
It really is the ultimate trump card in the race against urbanization. And because of that clean sweep, global demand is absolutely surging. We touched on Gujarat earlier, and it makes total sense that manufacturing hubs there are rapidly scaling up their capacity with these large tonnage press machines.
Yeah, they have to.
They're having to build immense industrial infrastructure just to create the tools required to build the rest of the world's infrastructure.
It's true, because we are quite literally running out of horizontal room on this planet. The global population is shifting into cities at an unprecedented rate. We know we need to build millions of units of housing, transit hubs, and entirely new smart cities over the next few decades.
Yeah.
So the central challenge of our era really is, how do we build that rapidly without sacrificing safety, structural integrity, or sustainability?
And you definitely can't build tomorrow's smart cities out of splintering wood and backbreaking iron.
You really can't. Highly reusable, highly recyclable, precision-engineered aluminum systems are the hidden foundation for sustainable urban development. It is the Goldilocks metal, fundamentally altered by thousands of tons of pressure, allowing us to build the future at the speed it's actually required.
It completely changes how you look at the world around you. Like, next time you walk past a bustling construction site and you see a new skyscraper that seemingly shot up 20 stories in a single month, you'll know there is no magic involved. You're just witnessing a highly choreographed ballet of precision extruded metal locking together to tame a chaotic liquid.
It's a massive leap forward. But before we finish, I want to leave you with a thought about where this all goes next.
Okay, lay it on me.
We've spent this time breaking down how extrusion technology allows us to create perfectly precise, reusable metal molds today. But if we connect this to the broader evolution of smart cities, what do you think is the next logical step?
I feel like you're about to tell me the metal is going to become self-aware.
Well, close. Think about it. What happens when we figure out how to embed smart sensors directly into these aluminum profiles during the extrusion process?
Oh, wow.
Right. We are already talking about hollow, geometric internal webs inside the metal. Imagine a future where the formwork itself actively monitors the temperature, the moisture levels, and the internal hydrostatic pressure of the concrete in real time.
So the mold itself could essentially text the site manager and say, hey, the liquid rock has perfectly crystallized. You are clear to peel me away.
Exactly. It would completely eliminate any remaining guesswork regarding curing times, which would further accelerate construction while guaranteeing absolute structural safety. It's just a fascinating frontier for where extrusion technology and digital infrastructure are going to meet.
A smart mold talking to the building it's creating. That is incredible. Well, thank you so much for guiding us through the physics, the scale, and the massive global impact of this hidden technology.
It was my pleasure.
And for you listening, we hope this exploration has given you a fresh lens on the built environment. The next time you see that wet gray sludge pouring out on a job site, you'll know the immense engineering it takes to tame it into the skyline we live and work in. Keep learning, keep asking questions, and we'll catch you on the next deep dive.